You are Nick, but if you prefer, we can change your role to attendee.
Okay, so I'm gonna start now the webinar, and then maybe give it 1 more minute, 2 minutes till all the participants are in and connected, and then Gorian, well, you start and introduce Umesh. Huh?
Okay, great. So let's get started. So welcome everyone to the first tutorial session of QCrypt 2021. So before we start, let me just remind you about how to ask questions. So there's 2 ways. One is to enter your question into Slack. And then I will be paying attention to that. And if it makes sense to ask the question at the time, I'll stop and ask the question. Otherwise, I'll read them at the end. And the other way is to raise your hand in Zoom, and then I will unmute you, and you can ask your question. Okay. So we're very pleased to have Umesh Vazirani here to give a tutorial to us. And Umesh will be talking about a very interesting new area at the intersection of quantum and classical cryptography, and that's classical proofs of quantumness. So please go ahead, Umesh.
Thank you, Carson. I guess good evening, everybody, or good morning, depending upon wherever you are. So let me just say that I'm going to try to keep this tutorial at a relatively high level. And so, please do feel free to interrupt with questions if you like. Let me start with trying to first say at an intuitive level, what's the main difficulty when you're trying to verify or validate a quantum computer. So the problem we have is this, that our access to this quantum computer is relatively small. So Hilbert space is exponentially large, and the quantum computer could be exponentially powerful compared to us as classical verifiers. And so if you look at these attempts at verification and validation, the central question that ends up, the issue that ends up being quite central is, how do you enforce a qubit structure on the prover's Hilbert space? So, and how do you enforce both an initial state as well as X and Z operators on these qubits? So in other words, what we want to do is we want to make sure that if you don't trust the quantum computer, the most difficult thing it turns out is how do you make sure that whatever operations the quantum computer is doing, they really are operations on individual qubits. You know, that there really are qubits that the quantum computer is operating on. Okay, so let me give you sort of a small you know, overview of what this new area is. So what it provides is a way that a classical verifier can actually constrain the quantum computer through the use of post-quantum cryptography. So in this sense, the post-quantum cryptography, in a sense, provides a kind of a leash on the quantum computer that restricts the sorts of things it can do, without actually restricting the quantum capabilities of the quantum computer. Okay, so how does this? What are the sorts of results that you can obtain through this? You know, there's a large number, you know, and a growing number of kinds of results, starting with a proof of quantumness, a proof that the quantum computer is indeed doing something quantum. You know, certifiable random number generation, classical verification of the result of that quantum computation, fully homomorphic quantum computation, meaning you know, classically delegating a quantum a computation privately to the quantum computer, and even something like device-independent quantum key distribution from computational assumptions. So where now you make sure that you have you know, as long as your classical cryptography is not broken during the protocol, then the keys that you get are information theoretically secure and random. Okay, so now just to give you you know, just to provide some background, you know, these kinds of results have been obtained before in other settings. And, you know, so for example, if you're trying to verify a quantum computation, then there are two other settings in which this has been looked at before. The first one is where there's a mildly quantum verifier, you know, where the verifier has a quantum a constant number of qubits of storage and a quantum channel to the prover. And in this setting, which you know, which was introduced by Aharonov, Ben-Or, and Iban, and Broadbent, Fitzsimmons, and Kashefi, the idea again is to randomize these qubits using the Pauli X and Pauli Z 12, and you randomize these qubits so that the quantum computer actually performs the computation under the covers. And since the quantum computer doesn't know how these qubits are encoded, it really doesn't have a possibility of deviating from protocol. So the qubits, you know, you enforce the qubit structure by virtue of the fact that the qubits have been encoded, and the prover doesn't dare to deviate from the qubit structure because it doesn't know what the qubits actually look like under the covers. There's a second setting where you have a classical verifier and you have two entangled provers, or two entangled quantum computers that cannot communicate with each other. And now this time you use the properties of entanglement, you know, of Bell inequality violations to enforce the qubit structure. And so you enforce this initial state that the two quantum computers share a bunch of Bell states, and they apply X and Z operators, X and Z measurements to them. And in fact, in this you know, there've actually been a lot of work on this. You know, so this initial work required polynomial in N CH/SH tests to enforce N qubits, and then there's this beautiful work by Natarajan and Vitek showing how you can use quantum low degree tests to actually reduce the amount of communication and testing to just polylog in order to enforce N qubits of entanglement. And then, of course, there was the more recent breakthrough, which takes this to the ultimate level by showing that you can use only constant amount of communication. Okay, so now let me describe to you the outline of this tutorial. So what I'll do is first I'll show you the very basic protocol, which is called the Qubit certification protocol, which is based on Trapdoor claw-free functions. And this is in the setting of a single of a classical verifier interacting with a polynomial time-bounded quantum computer or quantum prover. Now, I'll spend a little bit of time on this Qubit certification protocol because things get a little bit tricky there, and you know, in order to actually prove the correctness of this protocol, you need Trapdoor claw-free functions with a particular kind of property, which is called an adaptive hardcore bit. And we only know how to create these you know, TCFs with adaptive hardcore bits based on learning with errors. Okay, so then I'll talk about how this protocol gives you a proof of quantumness. Then I'll talk about one more thing that I think is it's simple, but I think it's very basic, and this is this notion of how do you enforce a qubit in the Hilbert space via Jordan's lemma. So this leads to randomness, the randomness protocol, and then what I'll do is I'll go through a few quickly through the verification of quantum computation, and then efficiency considerations in these protocols, how to do efficient randomness certification, and how to give a proof of quantumness without the adaptive hardcore bits. So okay, so these are things that I'll just touch upon lightly. Okay, so what's this Qubit certification protocol? So this is a protocol where the quantum computer creates a qubit, which is either in the plus state or in the minus state, and the quantum computer only knows an encryption of the bit C, which determines whether it's in the plus or the minus state. On the other hand, the verifier is classical, so the verifier has no ability to actually work with this qubit. But on the other hand, once this encryption is revealed to the verifier can use the knowledge of the secret key to actually figure out which qubit the prover is holding. And this turns out to be really the basic building block of all these protocols. So let me, what I'm going to do is work through this protocol and try to show you what, what are the, first in a simplified form, what this protocol looks like, and then then I'll try to go through some of the, some of the subtleties of it. Okay, so so trapdoor claw-free functions. So we are given a pair of functions mapping n bits to m bits. They are both injective functions, and we are going to assume that they have the same image, so that given any element in the range, they are exactly two pre-images. Okay, so now these are these functions have two properties. One is that it's computationally hard to find the claw. So you cannot find a triple x0, x1, and y, where x0 and x1 are the two pre-images of y. On the other hand, there's a trapdoor. So given, if you know the trapdoor, then you can efficiently invert y. So given y, you can compute both x0 and x1, which are the two pre-images of y under these two different functions. So these trapdoor claw-free functions were introduced by Goldwasser and Micali I believe in the 80s. And what we are going to be using is the post-quantum analog of them. So just using a post-quantum cryptography to implement these trapdoor claw-free functions. Okay, so let me just describe what this this basic qubit certification protocol looks like. So it starts with the verifier specifying what F is, giving some description of F. And then the prover responds with a string in the image, Y. The verifier issues one of two challenges: either the verifier asks for a pre-image or an equation. And so okay, so let's see what an honest prover does in response. So the honest prover starts with an equal superposition over 0x and 1x, where x is ranges over all the n-bit strings, and then computes f of x in superposition, either f0 or f1, depending upon this first bit. Then the prover measures the third register and returns that value to be y. So at this point, the prover has a superposition over the two pre-images of y. So if the challenge is 0, then the prover, of course, measures in the standard basis. If the challenge is 1, then the prover measures the second register in the Hadamard basis. And in this case, now what happens is that the prover is left with a single qubit, and the single qubit is in this state where the phase, it's an equal superposition of 0 and 1, but with this phase which is d dot x0 plus x1, where d is the result of that measurement. Okay, so d is what the prover sends back to the verifier. And now, since the verifier has trapdoor, has the trapdoor, the verifier can compute x0 and x1, and together with D that the prover supplied, the verifier now knows what this qubit looks like. Okay, but what we'd expect is that the prover has no idea what this qubit is, because the state of this qubit, because that seems to require knowledge of both of the pre-images. Okay, so now let me run through at an intuitive level why this provides a proof of quantumness. So here's the idea. A quantum computer can answer either challenge, as we saw. On the other hand, waving our hands slightly, we can say, well, no polynomial time classical or quantum computer can answer both challenges. Because answering both challenges seems to require knowing both x0 and x1. Okay. Now, there's something a little bit strange here, because this this second statement about is symmetrical in both quantum and classical. On the other hand, we are going to claim that what this shows, this second statement, what it implies is that no classical computer could possibly answer either of the two challenges, whichever one is asked. And the reason for this is that the classical prover can be rewound. So we could, if we asked, if we gave the pre-image challenge, then we could rewind the computation to just after Y was revealed, and then reissue the challenge 1 and get back the equation, get back D. So if it can answer either challenge, it can answer both, and therefore that that would break cryptography. So as I said, so far I said this somewhat informally, but let's look at what are the precise conditions we need for this whole thing to work. So for a classical computer to succeed, it must provide both one of the two pre-images, x0 or x1, so let's call that x, as well as okay, so okay, so let me I'm sorry, I have to change things slightly here just to make sure. So for the purposes of what I'm so there are two ways to run this protocol. One is where we are left with a quantum state at the end of the protocol, this qubit, and the qubit that the prover holds is determined by D. And the other way we can run this protocol is actually have the prover even measure this last qubit in the Hadamard basis, so that D now consists of all n+1 bits. And if we do that, if we do the second thing, where this last qubit is also measured, then we'd end up with this condition that D dot x0 plus x1 is equal to 0. So we'd actually get an equation. Okay, so what I'm saying here is that for the classical computer to succeed, it provides both an image as well as an equation which relates D and x0 and x1. Okay, so who said, so this doesn't directly contradict the claw-freeness of the trapdoor claw-free function. So in order to do that, we need to say that it's actually hard to hold on to a pre-image as well as this D, such that D dot x0 plus x1 equal to 0, or to know that D times x0 plus x1 equal to C. Okay, so this is based on so asserting that this is actually something that's hard to do is asserting a new kind of hardcore bit property. So the property that we want is that the knowledge of a pre-image X together with a better than 50-50 guess for D inner product with X0 plus X1 for any choice of D implies an efficient algorithm to find a claw and therefore break LWE. So the important thing here is that in this protocol, a dishonest prover can choose to give any Y of their choice, and then choose to give any D of their choice, and the choice of D in particular can be made after seeing the particular choice of the TCF and the choice of Y. Okay, so the fact that this is actually something that is hardcore, leverages these properties of LWE called leakage resistance, which provide a way of proving hardcore bits, sort of much more easily than previous techniques, and much more general settings, and so so one can sort of piggyback on those and prove even this kind of a hardcore bit statement. Okay, so let me try to since all this relies on LWE, let me just run through and describe LWE and how it's used in this context. Okay, so actually, before I do that, let me just stop and see if there are any questions. Okay. Okay, so so in LWE, we are given a random matrix A over ZQ. So let's say that we start with an A, which is a random M by N matrix, where M is, think of M as much larger than N. And we have a secret S, which is in ZQ to the N. Okay. And now the way we encode the secret, encrypt the secret S, is we take A times S and then plus a noise vector E, where the entries of E are chosen from a suitable Gaussian to be small entries, but the entries are sufficiently large to obfuscate, to make it hard to solve these linear equations, but sufficiently small to have S be uniquely defined in this process. And so the LW assumption says that if T equal to AS plus E, then this pair A comma T is computationally indistinguishable from A comma U, where U is a uniformly random vector. Right? Okay, so now, how do we get a trapdoor claw-free function from LWE? So we fix our LWE sample A comma T, And now the idea would be, well, we want F naught to just be, you know, so if we want to define functions F naught and F1, so we let F naught of X just be AX plus E naught, where E naught is chosen randomly from some Gaussian distribution. And for F1 is just AX plus E naught plus T, right? So we shifted by, F1 is just F naught shifted by this LWE sample. So now we have two issues. The first is that our functions now, well, the output is sort of probabilistic. It's a distribution, right? Because we are choosing E naught at random. Okay, so the way we deal with this problem is we just instead of calling it a TCF, we call it an NTCF for noisy TCF. The second issue is this, that, well, if we look at what the thinking behind this translation by T is, well, if we let this noise vector E in the LWE sample, if we let that be 0, then something nice happens, because F1 of X is just A of X plus S, A times X plus S plus E, right? Which is, and so F1 of X is F naught of X plus S. Okay. So F naught and F1, you know, so we have now this collision between X and X plus S. Okay, but the problem is that E is not equal to 0. And so you know, instead of getting this very nice relationship, we'll have F1 of X is A of X plus S, A of A times X plus S plus E naught plus E, and we don't know quite what to do with this. So the solution is to sample E naught from a much wider Gaussian than E, so that if you look at the two distributions, E doesn't change the distribution by very much, right? So the two distributions are almost the same distribution, except it spreads out just a little bit, so that the difference between the two distributions can be made arbitrarily small. It can be made polynomially small. Okay, so that's one way to, you know, that's a way to deal with it, so that then we can essentially assume that F1 of X equal to F naught of X plus S.
So Umesh, there's a question in Slack. Maybe I can generalize it a little bit. Can you just say a little bit about what here is public and what isn't? So for example, the distribution of E and E naught, are those, you know, known in advance to everyone, or,
yes.
You know?
So let's say that the only thing that's secret here is this S, right? Which is the particular sample that we are going to be, you know, how we are choosing the sample T. So everything else is public. A is public, T is public, you know, the distribution of E naught, E1, E it's all public. Okay, now one thing that that follows very easily from this definition is that you know, this is claw-free, and the reason is that X naught minus X1 is exactly S, right? Which is our LWE secret. And so if you can compute both pre-images, you've actually managed to solve this LWE problem. Okay, so now let's just make sure that the fact that our output is a distribution doesn't really create any problems for us. And in fact, all we really need to do is to check that we can create the superpositions that that the prover can create the kinds of superpositions that were called for earlier. And in fact, it's, it doesn't. Okay, so let's just do that. So we'll start off with a superposition over 0x plus 1x, x over all possible elements of ZQ to the n. And then we compute f, right? So we compute if this first bit qubit is 0, then we just compute ax plus e naught, right? E naught is now we take a superposition over this Gaussian, and okay, so that's what we do. And in the case that the first bit is 1, then we compute ax plus e naught plus t. Right? Now when we go ahead and measure this third register, we'll see some value y, which the prover will return to the verifier. And now, as you can see, these first two registers would now be in the superposition 0, x naught, 1, x naught minus s. This s is coming exactly from the fact that we had a times s over here. And of course, the fact that there was we were off by e doesn't really change things very much, because e is small. Okay, now there's a thing that you have to note here, which makes things quite confusing. And this is the thing that makes things tricky, both tricky in terms of working with these DCFs, but it's also something that makes them work out. It really plays a central role in all of this, which is, on the one hand, we are working mod q out here, right? So x naught minus s, we are doing these operations mod q as vectors. On the other hand, eventually for the protocol, we want to think of working on qubits. So we are really going to be representing each entry using log q qubits, right? So when we think about this x naught and x1, we think about actually taking each of the coordinates, and instead of writing down a number between 0 and q minus 1, we actually write it down in binary. And so we have so many bits of information. But now, since we are thinking of x naught and x1 as binary strings, it's possible to get confused and think, look, don't we have we have a superposition x naught of x naught and x naught minus s, and so shouldn't we be able to do a Hadamard and extract s from it? And the answer is no, because this minus here is done mod q, and so so you have to keep this sort of straight as you will. Okay, so now with that out of the way, let's try to look at what this adaptive hardcore bit looks like. So the idea is, the knowledge of, okay, so the adaptive hardcore bit says, given knowledge of the pre-image x, which is one of the pre-images, x naught or x1, and a better than 50-50 guess for d times x naught plus x1, for any choice of d, that implies an efficient algorithm to break LWE. Okay, so again, since x1 equal to x0 minus s does not mean that d times x0 plus x1 is equal to d times d dot s, right? That's binary versus mod q. But what's true, nevertheless, is that since we know one of the pre-images, right? So say we know x0, then we can use it to efficiently compute from d prime such that d prime dot s equal to d times d dot x0 plus x1. And this is something very simple that you can do by just playing with the fact that you know x0 and you know x1 equal to x0 minus s. So so in that single bit, for in each position, since s is a binary secret, right? We will know that there are only two possibilities about what how x0 change, subtracting of s changes the bit values, and so using that you can sort of figure out what d prime looks like. Okay, so now saying that you don't have a better than 50-50 guess for d dot x0 plus x1 is the same as saying you don't have a 50-50 better than 50-50 guess for d prime dot s. So at this point, essentially what we want to show is that d prime dot s is a hardcore bit for LWE. Right? And d prime still is going to be an arbitrary, we want to show this for an arbitrary d prime. Okay. Okay, so now so we want to show d prime dot s is a hardcore bit for LWE, and we want to specifically say that d prime might be chosen based on our LWE sample T. Okay, so what we are going to do is use this leakage resilience technique. So we replace, we can replace LWE matrix A with this so-called lossy matrix, which is of this form B times C plus E, where B and C are low rank matrices compared to A. And E is an error matrix to try to hide the fact that we use this that this matrix looks, has this low rank. And so the fact that these are indistinguishable is another instance of LWE itself. But now the advantage of this is that when you look at when you look at encrypting a secret S under A versus under this lossy matrix, well, under this lossy matrix, if you were even given C times S, because C is low rank, you can use the leftover hash lemma to say that any bit of S is still close to uniformly distributed, even given C times S, right? And in fact, you could even say that most bits of S look close to uniform simultaneously, even given C times S. So this is really a remarkable, I mean, for anybody who was involved in proving hardcore bits for explicit functions, in once upon a time in cryptography, this is just shockingly powerful and simple, this whole technique. Okay, so now now what one can do is, again, we can use the fact that we can use the binary nature of S and the Fourier analytic argument to prove that this is indeed an adaptive hardcore bit. Oops. So, okay, so so there are still okay, so let me just say what did I not cover, other than the obvious things, where I did not say exactly how you go from D to D prime, and I skipped this Fourier analytic argument. There's one other thing that I skipped, which is that for all this to hold, we must have D not equal to 0, right? And that imposes some condition on D prime. And that's something that we have to be able to check efficiently. And of course, that's something that you can check efficiently because the verifier has Trapdoor information. But once you go but then in fact it turns out that for the adaptive hardcore bit, you really do want that that argument really does require that it's a reduction. You don't want to have the key present, and so this introduces a different level of another complication into making these protocols work. So that's one other piece that I should alert you about, that if you really want to dig all the way into the details of this, you really have to worry about this condition that D must not be 0, and therefore there's a condition on D prime, and that ends up being a little bit tricky to work through. Okay, so I'm going to move on to randomness generation now, but let me see if there are any questions. And actually, also, let me just see how much time I have.
So, I mean, so there are no questions at the moment, but if some pop up, I will let you know. Officially, we end at, I guess, 6 Central European. So I think in like 25 minutes or so, but
okay.
But there's nothing kind of right after, so
Well, I'll try not to.
We're not going to run over anyone if we go on.
Okay, so yeah, great. Okay, so let me try to work through this. Okay, certifiable random number generation. So what in certifiable random number generation, what we're trying to do is start with a small number of random bits and expand that into a larger number of statistically random bits, together with some sort of a certification that this particular output bit must be random, even though we don't trust the quantum device that's generating that extra randomness. And so okay, so here's the idea about how to do it using this basic Qubit certification test. So what we do is we choose F pseudo-randomly. So we use a small number of random bits to generate F. Now, we are going to use the 0 challenges to generate randomness. So whether it's X0 or X1. And every so often, we'll use a 1 challenge to keep the device honest. So the amount of randomness we have to use up is the randomness to generate F, which is a small amount of randomness to create this F pseudo-randomly, as well as the random locations of the one challenges. So if we keep the number of one challenges down to a very small number, then that's going to then that would mean that the amount of randomness we are generating is relatively large. Okay, and the property we want is that if the prover is unable to break cryptography during the protocol, then this must produce statistical randomness. Okay, and so the idea behind this this protocol is that we want to show that effectively the quantum device must be measuring a qubit in the plus state, and in this in the standard basis, then it generates randomness, and in the Hadamard basis, we are just checking that it's in that state. Okay, so in order to do this, we have to characterize the prover's Hilbert space. Okay, and to do this, what we do is, we come back to this whole idea about how do you characterize the Hilbert space, or how do you ensure that there are qubits there. And so the way you do this is by saying a qubit is defined by two anti-commuting operators, x and z, any two anti-commuting operators. So in our case, we have these two measurements, whether d times x0 plus x1 equal to 0 or 1, and whether x equal to x0 or x1. Okay, so our hardcore bit property says that these two measurements are almost perfectly uncorrelated, right? Given one, you really cannot tell the other one, right? Even if you had a slightly better than 50-50 guess for the other one, you can then break LWE. Okay, so now what we're going to do is we're going to use Jordan's lemma to take the fact that these two measurements almost anti-commute to recreate the qubit, to show that, to locate the qubit in the Hilbert space. And this is something that's really quite, this is very simple, but it's also a very fundamental sort of maneuver in these in this entire literature. So this is what this is how it's done. So if you are given two projectors, P and Q, then Jordan's lemma says that you can, these two projectors actually define a decomposition of the Hilbert space into a direct sum of two-dimensional spaces. And these two-dimensional spaces you can think of as pairing up the eigenvectors of the two operators PQP and QPQ. Okay, so the way you would to see this is that if E is an eigenvector of PQP with eigenvalue lambda, then Q times E, which is F, which is in the Q space, is an eigenvector of QPQ with the same eigenvalue lambda. Right? So the picture that we have is that we have this two-dimensional subspace spanned by E and F, and Q maps E to F, and P maps F back to E. Right? And so this is one of the Jordan blocks, and the Jordan angle is this angle between E and F. Okay. So now, if you have a quantum state and we have these two measurements, these two projectors which are almost uncorrelated, well, then that means that on average, you know, the angle between these two, you know, if you look at a typical Jordan block, the angle must be very close to 45 degrees. So another way of saying this is, at the expense of ignoring a few of a small number of blocks, we can say that all the angles are very close to 45 degrees. And so if you want, we could distort the state slightly, we could perturb the state slightly and get all these angles to exactly line up to be 45 degrees. And so once we do that, what we've done is we've actually perturbed these two projectors slightly, and now these two projectors exactly anti-commute. And therefore they exactly define a qubit. And so if we now locate these, you know, if we stack these Jordan blocks on top of each other, what we've actually defined is some unitary change of basis under which you know, these two projectors can be the operators x and z acting on the first qubit, right? So this is a way to locate the qubit up to a unitary change of basis. Okay, so now let me just very briefly describe Urmila's result showing that showing how to verify an arbitrary quantum computation classically, right? So the difference now is that, okay, so the prover now, instead of creating an equal superposition over pre-images, now creates a superposition of their choice, you know, alpha 0 plus beta 1 on the pre-images. So by you know, by starting with alpha 0 superposition over all x, beta 1 superposition over all x, computing f of x, measuring to get y. And now this y in some sense commits to this superposition over 0 and 1. Now, and again, there's going to be either, you know, either pre-image or Hadamard test and so on. But now the prover is supposed to choose. Okay, so what's the prover trying to do? The prover is supposed to choose this sequence of n qubit state to be the ground state of a certain local Hamiltonian with only xx and zz terms. And computing this ground state is as hard as performing some arbitrary quantum computation of our choice. So this is the problem that the prover is actually trying to solve. Now, the difficulty is that now, since the qubit is no longer balanced, the Hadamard test cannot really, you know, the Hadamard test really cannot be performed as before. But on the other hand, it's possible to show, and this is really the crux of this entire proof, is that the prover cannot control the outcome of the Hadamard basis test, since you know, the Hadamard basis, sorry, the chooser. So what the verifier chooses is to perform either standard basis or Hadamard basis test, meaning a measurement in the standard or Hadamard basis, and therefore, you know, thereby sort of estimating the energy of these xx zz terms, you know, on as required. Sorry. And the idea is that the prover really cannot control the outcome of the Hadamard basis measurement. since it depends upon this D inner product with x0 plus x1. And the prover doesn't really know both x0 and x1. So that's the problem. But the important thing is that, even though there's not full control over this, what it's possible to show is that the prover's cheating on the Hadamard test is essentially equivalent to choosing a different superposition to start with. So essentially, if the prover cheats, then the cheating is limited to the following, that it's as though the prover, instead of choosing this particular superposition alpha beta, chose some other superposition alpha prime beta prime and answered according to alpha prime beta prime on both standard and Hadamard basis tests. And since the prover was completely free to choose any qubit state as their guess for the ground state, or an approximation to the ground state, they really have no reason to deviate from this protocol, as long as they can choose any state that they want, so they may as well choose the right one. Okay. Now, there's another way to get at this verification result. So Fitzsimmons and Kishefi had shown that if the verifier can force the quantum device to prepare one of 8 states, then you can verify an arbitrary quantum computation. And the 8 states are these, where you have an equal superposition of 0 and 1, except that the phase here is not just plus and minus, but these are these eighth roots of unity. Okay. Now the advantage of this is that now we have equal superpositions, and we can actually now start doing Hadamard tests and so on. So what Gregorio and Vidic showed is that you can use F8 instead of F2 for the Fourier transform to do the Fourier test, and you can use quantum random access codes to prove rigidity, and this whole thing actually ends up being quite an elegant alternative way of doing verification. Okay, so now let me in the brief amount of time left, I want to speak a little bit about further follow-ups having to do with improving the efficiency of both tests of quantumness as well as the randomness. So in terms of proofs of quantumness, one of the issues is this adaptive hardcore bit. So can we actually do this proof of quantumness without the adaptive hardcore bit? So I should emphasize here that this adaptive hardcore bit is really necessary for the randomness generation, because it seems quite necessary for the randomness generation, but here it doesn't seem necessary. So what one can show here is that what you can do is you can modify this basic protocol, the Qubit certification test protocol, to incorporate the CHSH game. Okay, so again, we just have a classical verifier interacting with a single quantum prover, right? But somehow within this protocol, you can incorporate the CHSH game, and where the space-like separation between the two players is replaced by this computational hardness of the crypto problem. Okay, so what this allows one to do is, one, you can now use a range of Trapdoor claw-free functions, including those not based on post-quantum crypto, because we are trying to give a proof of quantumness. So we are saying, well, either it's a quantum machine, or if it was a classical one, well, then it can't even break this. It definitely can't break this trapdoor claw-free function based on, say, x squared mod n. Okay, so there. I'm going. Let me just describe this this protocol a little bit, just so you can see how it works. So we started as always by the verifier sends the specification of the trapdoor claw-free function. The prover commits to a certain certain pair of pre-images by sending y. Okay, now the verifier either asks for a pre-image, in which case the prover measures x0 or x1 and sends it, or, so this is where things get different. Now we are trying to feed a hardcore bit to the prover. And so in an attempt to feed the hardcore bit to the prover, the specification we send an n-bit string R to the prover. Now the prover takes an extra register, an extra qubit, and computes R.x. So the prover ends up in this superposition, R.x, x0 plus R.x1, x1. And then the prover does a Hadamard on these n qubits and returns the result, which is D. So it does a measurement, and the measurement result is D. And now the prover ends up with a qubit in this state, R.x0 plus -1 to the D.x0 plus x1, R.x1. Now, you see the point is this. This state is either going to be in the state 0 or 1 or plus or minus, because it could be the case that R.x0 equal to R.x1 equal to 0, or it could be 1, or they could be different, 0 and 1, in which case this phase could either be plus or minus. And so now now the verifier specifies one of the CHSH bases, either pi by 8 or minus pi by 8, in which to measure this qubit, and that's what the verifier returns. And what one can show is that, again, in a CHSH-like proof, that a classical prover can achieve no better than 75% chance of success, whereas a quantum prover can achieve whatever, cosine squared pi by 8, just like in CHSH. And this ends up giving you a proof of quantumness.
So Umesh, we have a question on Zoom.
Yeah.
So Shashi, do you wanna ask your question?
I have a question about is the proof of quantumness is independent of the architecture of the qubit used, like superconductors, photon-based, etc.?
Yeah, the proof of quantumness doesn't, it's sort of treating the quantum computer as a black box, and it's saying we don't even know what the quantum computer is doing, right? So on the one hand, we are saying, look, if it's a genuine quantum computer, then it's following this protocol. An honest prover is following this particular protocol. But then what we're claiming is that a dishonest prover who is classical has no better than a 75% chance of giving the correct answer here. It's like the CHSH game. And that is independent of the architecture or what actually is being done. Okay, so let me also say, okay, so the one last thing I want to touch on is making this certifiable randomness more efficient. So this is something that we care about quite a lot because you know, that's a possible, you know, that may be the first interesting demonstration that one can actually give beyond proofs of quantumness. And certainly it's the case that these current, you know, like Google's quantum supremacy claim also comes with, you know, so for example, Scott has argued that, you know, based on certain assumptions, you know, some complexity assumption, maybe a very specialized, very, complexity assumption, that once you get this, through random circuit sampling, once you show that you pass the quantumness test there, you must be generating randomness. But that randomness, you know, the certification of it requires exponential time, right? Because that's how long that kind of quantum supremacy tests require. Whereas what we'd really like to do is get cryptographic randomness, which means that the verification process should be efficient. And so the efficient, so the randomness certification protocol I showed you before extracts at most 1 bit of randomness per qubit certification protocol, right? Per iteration of this protocol. And so what we'd like to do is actually make this entire process more efficient. And so here's a way to generate n bits of randomness by tweaking this qubit certification protocol slightly. Now, our intuition is that the original protocol should actually generate n bits of randomness, but we really don't know any way of proving that. Okay, so once you do this, once you actually generate these n bits of randomness, you can also use it as a test that your quantum computer has at least n qubits of memory. Okay. And so the test uses a very simple idea. It uses leakage resistance of LWE to choose this lossy version of the LWE matrix, which is now instead of being 2 to 1, we end up with a 2 to the k to 1 function, right? Because this lossy matrix has a small rank. The problem with using this, so now the idea is if you're using a 2 to the k to 1 function, and obviously the honest prover is going to end up with a superposition over 2 to the k pre-images, which means that you get k bits of randomness out of this potentially. The problem is that if you now, if you use this lossy LWE matrix, then the Hadamard test completely breaks. So now what do we do? Well, the solution is to use the lossy matrix for the pre-image test and the indistinguishable LWE matrix for the Hadamard test. So the protocol looks something like this. You take your lossy matrix, and if you intend to actually generate randomness, you send the verifier this lossy matrix plus a LWE sample for that. The prover commits to Y. You send back 0, saying I want a pre-image. The prover sends back a pre-image, which is now a random pre-image, hopefully. And then to test, what you do is you pick an LWE matrix and a sample, and you run through this protocol asking for an equation, and you check. Now, how do we prove that no matter what the prover does, the prover must generate about, theta of n bits of randomness. So the proof is quite tricky because, what we need to do is we need to use the computational indistinguishability between the lossy matrix and the LW matrix to say that the prover during the protocol couldn't distinguish and therefore must have generated statistical randomness, just the way, it should have happened. Okay, so the problem is that at some point we have to do this hybrid step, hybrid argument where we pass from a lossy matrix to an LWE matrix. And the problem is that in the Hadamard check, the verifier actually needs to have trapdoor information in order to actually do the check. And so, of course, if you have trapdoor information, the lossy and the LWE matrix are distinguishable. So one has to work around this by inventing a quantum verifier, a mythical quantum verifier, who actually doesn't need trapdoor information to actually check this Hadamard test. And then one passes through this quantum verifier, through the hybrid argument, and then to the classical verifier. And so that's as much as I should say about this particular result.
So Umesh, so just quickly before you go on, does the verifier extract the randomness from Y?
So the verifier could extract it from I. I think you could just say that X itself here should have high entropy.
Okay.
Right. Okay. Actually, so in the previous protocol, where the claim, the conjecture would be that Y itself has theta of n bits of entropy.
Right.
We really don't know how to prove that. Okay, so let me stop with the following thought. So there are these two areas of post-quantum crypto and quantum cryptography. Quantum cryptography where you use quantum bits to get information theoretic security and so on. I think that what's happened now is that there's this very interesting intersection between the two, where you use post-quantum crypto in order to guide and, in order to gain control over quantum systems, and this very interesting, there's been a sequence of not just the results that I've spoken about, but and having to do with verification of quantum systems, but also, a lot of associated, results having to do with trying to create quantum primitives like oblivious transfer using quantum communication and entanglement and so on. To me, it seems like this particular intersection, there's a bit of a, there's a real renaissance and a flowering in here, and just an explosion of results and interest in there. So and it includes the sorts of things that I'm talking about, but it's not even limited to that. It just goes well beyond that at this point, and it's really growing at a very a very fast pace. And so to my mind, this combination of crypto and quantum, and the way you can use it to interrogate systems and gain control and so on, this is a very interesting direction. I would expect much more to come out of this.
Great. So thank you so much, Umesh, for this wonderful tutorial. So we have several questions in Slack, so I'm going to read them to you if that's okay. So the first question is, to what extent do these verification protocols allow for noise in the quantum system? For instance, all algorithms discussed started with an initial pure state generated by the quantum machine. What if this is not exactly the case? Would the verifier call the machine non-quantum?
Yeah, so, well, you know, I guess there are two different regimes in which you can ask this question. You know, one is what happens before we have error correction. So certainly doing fault tolerance within all this is easy, and incorporating it is easy. The real issue is what maybe I think that the question is getting at is, what do you do pre fault tolerance? And that's where these efficiency considerations become very important. And the question is just, how efficient can you make these protocols, and how small are the resources, the number of gates and the number of qubits, so that exactly how many qubits and how small do the noise, the gate errors have to be before we can actually get through some of these protocols. I should also say that some of these protocols seem to have, obviously there's a computation that's to be done and you've got to get through it, but then there's some amount of resilience in there, because some of the computations don't have to be done quite exactly. There's some leeway, but these are all things to be worked through, both at the theory end and then translating it into actual numbers.
So a related question is, if you have any sense of what the minimal number of qubits is for probing quantumness.
Yeah, so, okay.
Physical here, I assume, is meant.
Right.
Is meant.
So I think that if you were to use just straight off-the-shelf LWE, you'd end up at something like a couple of thousand qubits. But then there are ways to improve that, and I don't have a definitive number yet. So we're still exploring some of these possibilities, and both between how what you could actually prove and what you could do heuristically. The hope would be to get down to a few hundred qubits. But possibly the other barrier would be just how many total operations you would need, and what kind of gate error you would need in order to get sufficient fidelity.
Right. So another question: how is the computational Bell test result related to self-testing of a single quantum device under computational assumptions? This is a paper by Medgar and Vidic.
Oh, I see. Yeah, I don't actually, I don't know off the top of my head. I think there's another there's another paper due to Colitangelo and et al. Having to do with device independent QKD under computational assumptions. And I think these are all, I mean, I think that they may be all, so I think the Medgar and Vidic paper is more focused on actually enforcing the qubit, right? So enforcing a qubit state, whereas I think this is maybe this is actually incorporating a Bell test into this, which is, I think, a little bit closer to the DI-QKD under computational assumptions.
So maybe I mean I can ask I think a related question to this. So I guess the soundness proofs for the proofs of quantumness are really showing that these are kind of proofs of non-classicality, right? Like they just show that a classical adversary can't win, but they don't show that if there's a winner, then he must be doing something quantum. So if that's what I want, then do I need to do these like self-testing protocols, or do I need to do BQP verification, or is there something simpler that I can do?
So in terms of a proof of non-classicality, right? So these quantum supremacy experiments, like random circuit sampling, etc. These are also not proofs of quantumness, but proofs of non-classicality, right? But those are being done at great expense, in terms of you have to do exponential computations to verify. So I don't know of a simple way of doing it, right? I mean, eventually, you have to do some computation that you have to say could not be duplicated classically, and which means either you could try to do integer factorization, but that's a long way off. So you really want to find as simple a computation as possible that you can duplicate classically.
So I don't see other questions. Maybe I'll give everyone a chance to ask. So I'll ask one more question, and then maybe in that time, that gives everyone else the sort of last chance. So maybe this is just a question about the cryptographic assumptions. So you talked about how LWE has this really nice leakage resilience property, and you're able to kind of get a lot out of it, get this adaptive hardcore bit, I guess also get this now constant round protocol for certified randomness. Is your sense that plain LWE really is kind of the only game in town for that? I mean, is everything else not leakage resilient, or do we just lack sort of techniques for showing that in fact some of them are?
I don't know the answer to that. I'm not an expert on that. I just know that having worked on hardcore bits in the 80s, when it required so much sweat and blood, and then I was not paying attention for quite a long time, and then when I turned around, there was this. From my viewpoint, it was an absolutely incredible technique. This was, so I was bringing an 80s perspective to this, and I was thinking that we had no right to expect this sort of riches, and so I'm maybe I'm still stuck in that time warp and thinking to myself, we have an embarrassment of riches here, which we had no right to expect or deserve, and so I wasn't even thinking that
we should ask for more.
but you're absolutely
Fair
right.
enough.
You should be asking for more, and it's the right question to ask.
Okay, well, I don't see any other questions, so let's all please, in whatever way you like, thank Umesh for this wonderful tutorial and for your time with questions and so on. If you're available, I think there is like a lounge after, if there's more people that want to ask you questions, but otherwise, thank you very much, Umesh. We really appreciate it.
Thank you. It's a great pleasure.
Yes, thank you, Umesh, for your nice tutorial, and also thank you for all the other speakers of the day. And yeah, this then wraps up, well, day one of the QCrypt conference this year. And I hope to see you all back tomorrow for day two then. Thank you. Have a good evening.